Hello everyone, welcome to the performance optimization techniques for mobile devices. This is an overview of the techniques, and you will see there's a lot of things to learn for people. Many people will know some stuff, many people will learn some new stuff. So let's move on to it. So about me, I'm an Ivica Bogosavljevic from Serbia. I'm an application performance specialist, and my professional focus is how to make programs run faster by utilizing better algorithms, better using the underlying hardware, using better programming language, standard library, or the operating system. I work as a performance consultant, so when people have problems with performance, I help them out to fix them, and I train teams when it comes to performance. Now, why do we focus on the performance and battery-powered devices, mobile devices? So battery-powered devices, mobile devices are now ubiquitous. You can find them everywhere, mobile phones, but also Internet of Things. And one of the requirements that is really important there is to conserve energy. Now, performance and energy preservation are somewhat related, so you will see how. And the topics of today, there are altogether five topics that we will cover today. The first one is how is performance connected, how are battery life and performance connected, how they work, how they appear together. Next thing, we'll talk about software design principles for battery powered devices. Some things are a bit differently when you're running on battery. Next topic will be performance optimization techniques, what to do and what not to do if you want fast software and if you want energy efficient software. Then we'll give some ideas for optimizing computational intensive codes and optimizing memory intensive codes. Now, don't worry if you don't understand what computational intensive codes and memory intensive codes are. We're going to talk about it very soon. So before diving into the battery life and performance, let's give a very simplified model of how CPU works on a battery powered device. So a CPU nowadays is mostly consists of several CPU cores. For example, my phone has 8 cores. One CPU core can either be running or sleeping. When it's running, it consumes full power. When it's sleeping, it consumes very little power. So this is a very simplified model that is sufficient for us. The CPUs can work. The CPUs can lower or increase the frequency, and with decreasing or increasing frequency, you will also see increase or decrease in energy consumption. But with this simplified model, it allows us to write efficient software. It's good enough for us. So how does that work? The CPU core wakes up, it does some useful work, and then it goes back to sleep. So, and why is performance important? Performance is important to maintain battery life. If your software is fast, the CPU can spend less time in running state and more time in sleeping state, and this lowers the energy consumption. Okay, now the first topic is the software design principle for energy efficiency. So these are the high-level considerations when you're designing your software to make it energy efficient. So all your data processing should happen at once. So how the component should be designed. It does some useful work, then it goes to sleep. If you have threads, they go to sleep for some time. You don't want to wake up your component too often, because if you want to, the longer it sleeps, the less memory it consumes. So instead of 1 millisecond, you want to increase the interval to 100 milliseconds or 1 second. Next thing, in your API designs, you want to avoid polling. So what is polling? Polling means asking other components if the state has changed. So often in embedded system, you will see that there is a check if the components have finished something, to check if there is something arriving on the input buffer and so on. So instead of doing it like this, register for events, register for callbacks to save power. Next thing you want to do is you want to avoid chatting with other local or remote components. So what chatting means? Chattiness with regards to software designs mean components that talk a lot, they exchange a lot of information. If two components exchange a lot of information, that means that that means that the components are chatty. When this happens, this has a tendency to increase energy consumption. And the most important part of how to preserve energy is to strive for high performance processing. And this is what we're going to talk about today. Now, just for the record, this is not only specific to embedded systems, but also specific to desktop systems even more, is that the CPU is almost never used completely 100%. But the CPU's resources due to various bottlenecks, and if you know where the bottlenecks are and you can help it increase performance, this is important for embedded systems, because sometimes you might be considering to buy another chip because the one which you have right now is not fast enough, but maybe you should ask yourself another question. Is my software performant enough? Okay. So what is the way of the performance on mobile devices, or generally on battery-powered devices, or all devices that are somehow limited in energy? So in desktop settings, especially in high-performance computing settings, they have like these huge servers with many CPU cores, and then they use the brute force approach to distribute the workload to several CPUs. So if you have this, like you have some hot loop, which takes like 5 seconds, if you distribute it to 4 cores, if you're lucky enough, you can get 4 times speed up. Now, this doesn't work very well on multi-threading. Is not always a good idea on mobile devices, because with each core consumes energy, and this code actually consumes more energy than the single-threaded code. Now, multi-threading generally increases energy consumption. It is difficult to do if 4 cores are not equally fast. And on CPUs, we often see designs where there is this imbalance that some cores are faster than the others. Next things, mobile devices often have limited memory bandwidth. So the CPU and memory, they're connected with a bus, but it has a limited bandwidth. And what happened is that even all CPU cores are busy, but most CPU cores are waiting for the data to be fetched from the memory. And this actually increases memory consumption without doing any useful work. In my experience, a well-written single-threaded algorithm often can outperform an evilly written multi-threaded algorithm. But bear in mind, this is one assumption is the multi-threading actually increases energy consumption. But if it's done good, it doesn't necessarily mean that your program will consume more energy. If a loop takes 10 seconds to execute on a single core and 2.5 seconds to execute on 4 cores, then it's worth considering using multi-threading to distributing it to 4 cores. Wouldn't bring any additional increases in energy consumption. So a good indication for multi-threading on mobile devices is when the speed up is linear to the core count. If you have four cores, that means your software should be running 4 times faster. Okay, this is end of the first topics. Any questions?
Yes, there just came a question in. As multi-threading consumes more energy, is the reason why Apple Silicon has extremely high single-thread performance, but only on average multi-threaded performance? So
I'm sorry, I don't know how Apple designed their M1 silicon, so yeah, I don't know. I don't know the answer to that question.
I think it's an interesting question, but it's outside of the scope of this talk.
But let me just give you a general explanation, which is valid for all architectures. You have CPU cores, and you have CPU speed, and you have memory, and you have memory bandwidth, the amount of data you can fetch from the memory. Now, if you have a really fast cores, but the memory bandwidth is not large enough, in that case, you will see less benefit from multi-threading. And vice versa. If you have slow cores, but you have a lot of memory bandwidth, then you can achieve like linear speedups up to 48 or 256 cores that run software that runs 256 times faster. To be honest, I was surprised. For example, I have Raspberry Pi, the board with ARM Cortex A72, but the same chips is also the same core is also used in a high performance cluster. The same core, so I think they're the same silicon. What is different is that my Raspberry Pi has a really low bandwidth over memory, and the software there, multithreading doesn't scale well. On that high performance system, it scales almost perfectly. Okay. Next, we talk about better using the hardware resources. So if you're aiming for peak performance, and that this is what you want to do in case that you're aiming for reduction in energy consumption, you want to write your programs so they use hardware resources optimally. Now, from the viewpoint of hardware resources, there are two major bottlenecks. The first bottleneck is if your program is limited by the amount of calculation it needs to do on the CPU. So CPU has some resources, dividers, adders, vector units, and so on. And if the bottleneck is in the CPU itself, we call this code computational intensive, or we say that the code is core bound. Alternatively, if the problem is not in the CPU core, but the problem is in the memory bandwidth, the amount of data you can get from the memory, we call these codes memory intensive, and we say that the code is memory bound. So why do we introduce these two new terms? Because the optimization strategies for computational intensive are completely different from optimization strategies for memory intensive codes. Okay. Now the question is my code computational intensive or is it memory intensive? Is its bottleneck in the CPU or its bottleneck is in the memory? Now, there are tools that you can use like Intel's VTune profiler, AMD MicroProf also has some mmap, PMU tools, Perf or Liquid to read the hardware performance counters. Now, these hardware performance counters can tell you if this code is more waiting for memory or it is more waiting, doing some processing internally. Now, if you use these tools, you will see that memory-intensive codes will typically have bad numbers in memory-bound section. So there is this data cache miss section, and it will be bad. You will see the bad numbers there. Now, computational-intensive codes will typically have bad numbers in the core-bound section. That means that there will be high use of vectorization units, high use of dividers, a large amount of branch misprediction, and so on. Now, these tools are not so simple to use. They have a steep learning curve because you need to know the hardware architecture and so on, and it takes some time to master it. But luckily, there is like a way to determine if your code is computational intensive or memory intensive by just looking at the code. Okay, questions until this point?
Yeah, so right now I don't see any questions, and I think we can carry on.
Okay. So we'll talk now about how to optimize your computational intensive code. So just this. Just a second. Wait. Okay. So when is the question is is my code computational intensive or is it memory intensive? Now, if you have a loop that is processing simple data types like integer, chars, doubles, not classes, simple data types, or maybe smaller classes, but not large classes. If the data is stored in an array or a vector, so vectors and arrays are basically the same, and you're accessing neighboring elements of the array sequentially. So you're going inside the array, you go from 0 to n or from n to 0. So then your code will be computational intensive. It will most likely have a bottleneck inside the CPU itself. Now, if any of this is not true, then your code will be memory intensive. This is important to note. Not many codes are this. There aren't many codes like this. So codes that are processing simple data types and data is stored in an array, and you're accessing it from sequentially, but not skipping any elements, not doing any random accesses. There aren't many codes. These codes happen a lot in like scientific computing, image, audio, and video processing, machine learning, especially matrix multiplication, telecommunications, and so on. But in the general object-oriented programming world, they don't happen often. Now, if any of this is not true, if you're processing large data types, so data is stored in a hash map or a tree, or it is stored in an array, but you're not accessing sequentially, but with a stride, for example, element 0, element 8, element 16, and so on, your code will most likely be memory intensive. Now, the question is, so this is part of the computational intensive topic, is fixing memory intensive codes. What does that mean? On some occasion, there are certain transformations that you can do on your code, on your loops, to convert memory intensive codes to computational intensive. And it's much better to be computational intensive because the memory is much, much slower than the CPU. CPU is really fast, but far too often it has to wait for the data from the main memory to arrive. Now, the first way of doing this, so fixing memory intensive code, is called structure of arrays. So what is it? Let me give you an example. So we have here a class student, which has a string, which is a name, and a double, which is an average mark. Now, there is a vector of student classes, and the question is, how much time do we need to calculate average mark for all students? So this is the first way of representing it. Class with name and average mark. The second way of representing is that we have class students. Please notice the plural here. And then we have one vector for names and the other vector for average marks. Now, these codes, this is object-oriented code. It's called array of structures. So, and this is not object-oriented because each member of the class has its own vector, and it's called structure of arrays. This transformation from array of structures to structure of arrays actually increases performance. And if you want to calculate average mark of all students, original code takes 194 milliseconds, and after this transformation, it takes 42 milliseconds. Now, question is why? Because in this second case, we are only accessing this vector, and this is a vector of simple types, and we are accessing it from 0 to the end. So this means that this code is computational intensive. In this case, we are accessing classes, and as we said, classes are not primitive type, and this code is memory intensive. Okay, this was one way of fixing memory intensive code if you're using structs or classes in your code. Now, the second way of fixing memory intensive code is if your program is processing data in a matrix. So you're doing matrix processing. So this happens with linear algebra, or it happens with image processing. And if you're running through the matrix column-wise, so if you're processing matrix row-wise, going from left to right, your program is, and you're using primitive data types, this is computationally intensive. But if you're going column-wise, so you're going column-wise, this code is memory intensive or memory bound. Now, can it be fixed? Yes, it can. So here is on the left is an example of memory multiplication program loop. So we have 3 loops. Now, if you have a look at this, let's look at the side of the loop. So there are 3 arrays, C, A, and B. Now, this innermost loops iterates over K. With regards to that, access to C, I, J is constant because the K doesn't involve K. Access to this element is also constant. Inside the loop, we are also always accessing the same element. Access to this array is sequential. We are accessing neighboring elements, okay? Because the K is in the right brackets. But the access to this element, this array is, or this matrix is column-wise because we are indexing columns, not rows. So we are moving column-wise. So we move row 1, row 2, row 3, row 4, but the column remains fixed. Now, we don't like that. This access makes this code memory intensive. Luckily, there is this transformation called loop interchange, where we exchange the loop. We move the inner loop to the outside and outer loop to the inside. Now, if we analyze this code, what happens here? This is a sequential axis. This is just like accessing a vector from left to right sequentially. This is also sequential axis. This is a constant axis. The variable j changes, and this axis remains constant. Ik remains constant, doesn't depend on j. And this one is also sequential axis. Now we have 3 sequential axes and 1 constant axis with this loop interchange. Earlier we had 2 constant axes, 1 sequential and 1 strided axis. And this got much faster. So with this transformation, the program is accessing memory location sequentially, and we see that the matrix size 1200 times 1200, the first loop takes 5.8 seconds, and the second takes 1.22 seconds to execute. Okay, any questions until this point?
I don't see right now any questions in the chat to this.
Okay,
So,
moving on.
yes, I see we're moving on. Yeah.
So the previous two, the techniques, so loop interchange and the structure of arrays are used to fix memory computation, memory intensive codes. Now I'm going to introduce vectorization. So what is vectorization? Vectorization is really important if you aim for peak performance. So many modern CPUs can process more than 1 data in a single instruction. So they have these vector instructions. This model is called SIMD, single instruction, multiple data. Now the good thing about SIMD is compilers can these instructions are faster than their scalar version. So they're vector instructions and scalar instructions. These instructions are generally faster. The code which uses them works faster. And the compilers can automatically generate code that uses SIMD instructions if some conditions are met. So here's a simple loop on the left, which is A of I equals B of I plus C of I. When the compiler auto-vectorizes this loop, what it happens? So we see that the loop doesn't do I++, it does I plus 4. So it means it's processing 4 elements in each iteration of the loop. What it does, it loads 4 elements from the array B. Then it loads 4 elements from the array C into vector registers. So these are vector registers. Then it adds together B and C, 2 vector registers, and adds them together to this vector register A. And then when this results is calculated, it stores it back to the memory using this store 4. Now all the time it's working with 4. Each iteration works with 4 elements simultaneously. Okay, so using vector instruction is much faster. So the vectorized code runs typically 2 to 6 times faster than its non-vectorized counterpart. And the compilers can actually auto-vectorize loops when certain conditions are met. If the compiler has managed to automatically vectorize part of the code, that is a good indication that your code is running at maximum possible speed. So even if you disable vectorization or your CPU does not support vectorization, the fact that it was auto-vectorized earlier means that the code is well written. Now the question is, you want to ask yourself, did the compiler automatically vectorize my code? And you can check that. You can specify compiler flags for Clang. This is the compiler flag for Clang. And for GCC, this is the compiler flag for GCC. And it will tell you if you look it up, you will see that if your loop was vectorized, and if not, then it will tell you the reason. Okay, now the compilers, as I said, can vectorize certain vectorized hot loops, but the question is, what are the conditions for the compiler to do this? So in order for the compiler to vectorize your code, you need a good memory access pattern. So you need to use vectors or arrays, and need to go from 0 to n. You need to access sequentially, your arrays sequentially. So loops which access arrays but not sequentially don't vectorize well. They don't get any performance benefit from vectorization. Also, the loops that access memory in the random access fashion, like hash maps, binary trees, linked lists, so on, they don't vectorize that. Next thing is you want your loops to have independent iterations. So what is an independent iteration? Then that means that the current data you need in the current iteration does not depend on the previous iteration. If it does, we say the loop has data dependency, and these loops are impossible to vectorize. So sometimes there are loops that are impossible to vectorize. Next things you want to make sure is that the number of iteration is known before the loop starts. So what does this mean in practice? That means that for loops within where the start and end indexes are known and compiled are known at before the CPU enters the loop are good candidates for auto vectorization. If you have a loop and you break outside of the loop, or you're skipping iterations with continue, those loops don't vectorize well, or don't vectorize at all. Next thing is that you don't have a lot of conditionals inside the loop. So why is this important? If you imagine your for loop and you see a lot of conditionals, when you have conditional, the nature of vectorization is that your program is performing the same kind of operation on all its data. So if you're performing on all data the same operation, vectorization makes sense. But with conditionals, that means that different operation can be done depending on the data value. For example, you can do addition on positive elements of the vector and subtraction of negative elements of the vector. These loops don't vectorize well because you cannot generate, the compiler cannot generate vector instruction for them. And the last thing is that there is no pointer aliasing. Now, the topic of pointer aliasing is huge. But what does in essence mean is that the pointers, so the blocks of memory accessed through the pointers are independent on one another. If they overlap, then those loops cannot vectorize well. Okay, now, any questions about auto vectorization?
Yes, we do have two questions.
Yes.
The first one is, how do you identify code sections that need to be optimized for power consumption?
How do you identify optimize sections that need to be for power consumption? Now you use profilers. Those code sections will appear in the profiler with the longest runtime. Profilers are tools that programmers use to see which code takes the most time in their program.
Peter Wolf asks, regarding techniques like the loop interchange to auto vectorization, are there analysis tools which would help to detect classes or cases where the developer could optimize the loop?
So as far as I know, there is one tool which is developed by Pentra. It's called Paravor Analyzer, and it can detect places where you can use loop interchange. Clang has like a built-in support to detect places with loop interchange and do loop interchange automatically for you. But that code is experimental, and in my testing, it didn't work. So there were examples where you can see clearly there is a loop interchange, but it didn't detect anything. So if you're analyzing for loop interchange, the main question if you want to know if your code can profit from a loop interchange, the main question you should ask yourself is, am I accessing this element every time the inner loop increases by 1? Is this the index also increases by 1? So in this case, it doesn't increase at all, doesn't increase at all, increases by 1, increases by number of columns, for example. So this is the if you're doing manually. A Pentra tool can also do that, but I don't know any other tools that can do that.
There is one more question about indexes. When you are saying access array sequentially, do you mean iterate by index by index?
So it means that if you're accessing array, it means that if you have a for loop, you have the increment is I++, and then you're using this I. So if it's I plus equals 2 or I plus equals 8, that's not sequential. You have a stride which is bigger than 1. So sequential means basically going from 0 to n or from n to 0. That's also fine. I minus minus also works. But you should not skip elements. If you have array, if you skipping over some elements, then you're not accessing it sequentially.
Okay. That's all the questions on this segment. And
okay, now what are the fixes for vectorization problems? If your critical loop doesn't vectorize because there are too many conditionals or the loop is too complex, there are techniques like loop fission. Loop fission means splitting loops into vectorizable and non-vectorizable parts. And you can use this if inside the loop you have conditions, but they do not depend on the data. If the conditions are constant inside the loop. For example, if you have a loop and there is a if debug prints something and this debug is constant, doesn't change inside of the loop, then you can move it out. The compiler does that for you also. It's called loop unswitching. Also, if you have conditions that depend on the iterator variables, then you can do like loop peeling. You can peel a few iterations or do loop unrolling. There are also some ways to get rid of conditionals, but the essential conditionals where the processing depends on the data, you cannot get rid of them. So if you're leaving, I'm giving you the fixes for vectorization problems, but I'm not going into details because it would take too much time, and this is just an overview. But in case you come across a situation you want to optimize your loop, which is hot, takes a lot of time, this is a good place to start. Now, if you're leaving the loop earlier, if you have a search loop, so with the search loop, you don't know the number of iterations in advance. When you find something, you break the loop. So this loop is uncountable. There is a technique called loop sectioning that will allow you to vectorize the loop. If you have bad memory access pattern, then you're out of luck. If you can apply loop interchange or moving to a structure of arrays, that can help. If not, then your code will be memory bound. And the last thing is pointer aliasing. Now, sometimes the compilers are not sure if there is pointer aliasing. They cannot do this analysis. They cannot make sure that the blocks of memory are independent of each other. Now, you can use this restrict keyword to mark the pointer as independent of one another, and that unlocks the vectorization. Now, what you actually will do, you will take a look at the compiler optimization report, then you'll take to the Google, look it up and see what does that mean and how you can fix it. But these are generally recommendations. Okay, questions?
Looks like we have no questions this time. So
okay.
I guess we carry on.
Okay, next thing is optimizing memory intensive codes. So memory intensive codes, we talked about computational intensive code. Now memory intensive codes, what's that? So CPUs are much faster than the memory. And what happens is, and this happens a lot, is that CPUs have to wait for the data to be fetched from the memory. So the CPU designers did the following. They added a small fast memory called the data cache memory. And this memory is inside the CPU. And it is used to speed up access to the commonly used data. So if you're accessing a piece of data which is already in the data cache in the CPU, this access will be fast. But if you're accessing a piece of data which is not in the data cache, that means it has to be fetched from the main memory, and this access will be slow. So many programs, especially object-oriented programs with large classes, use memory inefficiently. So they have bottleneck and they're memory intensive. If you're aware of how the memories work and how data cache works, then you can use this knowledge to make to create more efficient access. Okay, so now question is, when do the data cache misses typically happen? So data cache misses are connected to lower performance. Data cache hits are connected to higher performance. So there are certain situations where data cache misses are more likely to happen. So what are these situations? So inside your C++ or C or C++ code, if you're dereferencing a pointer for the first time, so it's a very common operation using operator arrow. So this is the operator arrow. So if you have a classes, we have pointers to other classes. Every time you reference a pointer, you'll get a data cache miss. If you're accessing heap allocated objects, so for the first time, so you're accessing something allocated on the heap. If you have a vector of pointers, which are used for polymorphism, like row pointers, shared pointers, unique pointers. Next, if you have lookup in std map, std unordered map, std list, std set, and so on, all tree-based, link-based, and hash map-based containers, you will get data cache misses, because lookup in these containers actually the referencing using the arrow operator. Lastly, iterating through std list, not only lookup, but iterating through std list, std map, or std set will create data cache misses. Iterating through hash sets doesn't create data cache misses, can be made to not create data cache misses, because hash maps store their internally use arrays to store data. When do also data cache misses happen? If you're accessing a member of array or another data structure in a random fashion. So here is an example of loop. We are accessing this array histogram, but we are not using I to reference it. We use A of I. So histograms are often seen in image processing and scientific computing. Also, if you're doing a binary search, so binary search is done on an array, but you're not accessing sequentially, you're accessing randomly. You go in the middle, then you decide to go left or right. So this will also create data cache misses. Lookup in a hash map or a binary tree will also create data cache misses. Now, this creates data cache misses. The question is, when do data cache hits typically happen? So there are certain situations where data cache hits are more likely to happen. So if you're iterating through an array or a vector sequentially, we already talked about it. The smaller the type, the higher the chance of cache hit. So if the class size is smaller, this increases data cache hit rate. If the class size is larger, this decreases data cache hit rate and means lower performance. So rule number one of peak performance is that peak performance is achievable only when working with arrays and simple types or small classes. When the data cache also more likely to hit. So if you keep your data set small, if you have small hash set or a small vector or a small binary tree, this increases data cache hit rate. So lookup in a small tree or hash map is much faster than lookup in a large data structure. What also increases data cache hit rate? So what is accessed together should be close neighbors in memory. So if you have a class and you have two members inside the class that you often access together, you should declare them in the class declaration one after another. This increases data cache hit rate. What else? What is accessed one after another temporarily? So in time, if you access this element and then you access the next element, it should be laid out in memory one after another. So nodes of a linked list that are accessed one after another should also be one after another in memory. Also, this applies also for the binary trees. Nodes of the binary tree that are accessed one after another should be also one after another in memory. Okay, so this is about data situation which increase data cache hit rates or decrease data cache hit rates. Now, how do these recommendations translate to everyday development? So these were like generalized recommendations. Now, let's see a few examples and measure the performance difference. But with performance, you should always have in mind to always measure. Sometimes you assume something increases performance, but when you measure, it doesn't. So first example is minimum and maximum in array. So we have a minimum and maximum in a vector, which has a vector of class size 16 bytes, and there is 100 million elements in the vector. So if we are finding minimum and maximum in the same loop, it takes 207 milliseconds. If we are finding first minimum in one loop and then max in separate loop, it takes almost 2 times slower. So the question is, why such difference? iterating over the same data set 2 times wastes memory bandwidth. So what you should do is, when you're iterating over the data set, you should always strive to do as much work as possible. For example, STL offers STD and min-max to find both minimum and maximum at the same time. It iterates over the vector only once. Okay, this was the first example. So we see like double increase in speed just because we are iterating over the container once instead of twice. Next example is linked list memory layout. So we have this linked list which has 6 nodes, 6 values, but we have like, this is how it is laid out in memory. So we have, first it's called a random memory layout. So the nodes are just randomly just put in memory. They're just random. There is no pattern here. The second is compact memory layout. So they're compactly packed in memory. They take there is no wasted space between nodes, but they're not neighboring. So this is the first, then we go to the second, then we go to the third, then we go to the fourth, then we go to the fifth, then we go to the sixth. So they're not neighbors in. So the logically neighboring nodes of the linked list are not neighbors in memory. And then we have this called perfect memory layout. With perfect memory layout, linked lists that are logically neighbors that go after one after another are also logically, physically neighbors in memory. Now, which layout is best if you want to iterate over the list? That's the question. And the answer is depends. So we measured for 3 sizes of linked lists. So small size had 128 doubles, medium has 1 million, and large has 64 millions. And then we use 3 layouts: random layout, compact layout, and perfect layout. Now first, for small linked list with only 128 doubles, the layout is not important. The numbers are almost the same. But for medium and for large, there is a huge difference. Now, the random layout for the medium is 8.2, and compact is 6 seconds. And the perfect layout is 0.12 seconds. It's almost 50 times faster. For a large linked list, the random layout takes 15 seconds, and the compact 9.7 seconds. And the perfect layout doesn't change. It doesn't change. It doesn't depend on the linked list size. It remains constant. So for a small linked list, the layout is not important, but for a large linked list, a random memory layout is 125 times slower than the perfect memory layout. Now, the question is, okay, this is all nice to know, but can we control the memory layout of the linked list? And actually you can. If you use a custom allocator for your linked list, then it's possible to control memory layout. And if you put enough effort, you can achieve perfect layout and achieve perfect performance. You can find more info on my site in this post. So the question is, why is perfect memory layout the fastest? But there are several things to it. The CPU has a component called data prefetcher. That's part of the data cache. The data prefetcher can figure out the memory access pattern of the program, and then it can preload the data from the main memory to the data cache before the program even needs it. So if the CPU can predict the memory access pattern, it can preload the data. For vectors and for arrays, it is trivial to figure out the memory access pattern. If you're going sequentially over arrays or vector, it's really simple, and the CPUs utilize this. So when we are using perfect memory layout, actually the pattern, the way the CPU access memory is predictable for the CPU, and CPU can preload the data, and then you see perfect speed. Okay, questions until this point?
Yes. So I think like your comparison between list and vector is good, but what you should have, even with a perfect layout for list in mind, that there is like an overhead in the memory for list.
Yes, of course. I mean, performance is always at odds with some other things like maintainability, simplicity, and so on.
And
yes,
there's a question from Burkhardt. is the perfect layout for a list the same as vector? How are the performance numbers for std vector instead of std list?
So the problem with linked list, if you use like raw linked list from the standard library, is that you don't have any guarantees of the memory layout. It can be perfect, but it doesn't have to be. And normally, what you will see often is that if you have a small program, linked list is almost as fast as array. But if you have a large program which uses allocator a lot, so you have other components that are allocating the allocated memory, then you don't get the perfect memory layout. You get the bad memory layout. And what happens that is you get the performance drop significantly. Now you can fix this by using a custom memory allocator for this hot data structure that you want to keep perfect. But with the STL allocator, with the standard library allocator, there are no guarantees. You might two consecutive calls of malloc might return neighboring memory addresses, but there is no guarantee.
Okay, so we are slightly over time. I can give you like 3 to 5 minutes more. So,
okay. Let's see what to skip. Let's see like this. So let's compare a vector. Okay, let's do it quickly. So we have a vector of pointers, and again, vector of pointers. There is a perfect optimal layout or perfect layout where pointers point to the neighboring elements in memory. And there is a non-optimal layout where pointers just point to random pieces of memory. Now, this is the same problem as with linked lists. And if you compare the numbers, the runtimes, but perfectly optimal layout will be 384 milliseconds, and perfectly non-optimal will be 5 seconds. So it's like 10 times slower or 15 times slower. The problem of memory layout becomes apparent again. So if you have vector of pointers and you want to use them because of polymorphism, then you should consider vector of values, and they're much better for performance because the memory access pattern is predictable and the data prefetcher can fetch it faster. Also, there are no calls to malloc and free and the other things that are slowing it down. Now, the other thing that's also another example of how performance depends on the memory intensive code is this experiment with class size. We have this class rectangle and we're doing some processing on it. Now, how does the speed of processing data depends on the size of the class? So we have a class which is size 20 bytes, but then we grow 24, 28, 32, and so on. The size of the class grow. And you can see here that there are two different methods. One is calculate surface visible, the other is calculate surface all. But you can see that the performance gets worse as the class size grows. And when the class size is really large, the performance like 2 or 3 times slower than when it's really small. And when you have that, then good problem decomposition. You should only, if you have a hot loop and you have a class, you're processing classes in hot loop, then you should have, your class should be really small and you should access all the elements of the class, all the members of the class if you want maximum performance. So this is related to the data class size and performance. Why is processing of smaller classes faster? Well, the answer is simple. The data is brought up from the main memory to the cache memory, typically in blocks of 64 bytes. It's called cache line size. With large classes, the CPU is bringing data from the main memory to the cache memory, but this data is not used anywhere. So the data is brought to the CPU, to the data cache. The CPU can really access it really cheaply, but it's never used. And this is wastes memory bandwidth and slows down your program. If you have a code on the hotpad, moving all non-essential data to other classes will help the performance. Additionally, data members that are often accessed together should be declared together in the class definition, because this increases the chance that the data members will land in the same data cache block. Okay, other ideas for optimizations. We talked about linked lists, we talked about vector of pointers, but also other random access structures like trees and hash maps will benefit from improved memory layout. If you have random access data structures like trees or hash maps, keeping the the block of memory used by the data structure as compact as possible increases performance. These kind of structures where all the data is allocated in one block is called flat data structures. And there's like flat hash map, flat binary tree, and so on. Additionally, in case of binary trees, you can use a better memory layout. There is something called Van Emde-Boas layout, which is famous. You can Google it. And using this kind of memory layout for your tree increases performance. Or you can use n-array trees instead of binary trees. So n-array trees are generally more cache friendly. If you have a hash map that is slow, you can switch to a more cache-friendly implementation. There are hash maps with open addressing, and these are faster. They can be faster, they can be also slower, but if you are careful, they can be faster than the regular hash maps. STL implementation of binary trees and hash map is not the fastest, and there are faster alternative. Example, EA, the game producer, has its own implementation of the STL that aim for performance. Okay, so let's make a summary of the memory performance. For good performance, it is essential to use the available memory bandwidth in the most effective way possible. Avoid random memory access. Prefer vectors whenever possible. Avoid vector of pointers. Prefer vector of values. Keep things you use together close to one another in the memory. Keep data you're processing small. Classes you're processing small. Avoid rereading the same data from the memory several times. With a few exceptions, most of the software that you are writing or working on in the object-oriented paradigm is memory limited. And mobile devices typically have slower memories, smaller data caches, less memory bandwidth, so this makes the situation even worse. But with careful programming, you can achieve reasonable performance even on mobile devices. That's it.